Bode diagrams is one of very important tools which can be utilized for the analysis and design of control systems. And many times we do not have software tools with us. Therefore, it is very useful to learn how to sketch Bode diagrams by hand. So we have already talked about Bode diagrams for first order transfer functions. In today's lecture, we shall talk about Bode diagrams for second order transfer functions and for complex transfer functions. So a general second order system is given by this transfer function. To obtain the frequency response of this system, we substitute S equal to j omega. So this is the frequency response of this system. And Bode diagram is the plot of magnitude frequency response and phase frequency response. The same transfer function is rewritten over here. We have divided both the numerator and denominator by omega n square. So we get 1 over here. This omega n square divided by omega n square is equal to 1, which is written over here, and this term is written over here. We have simply divided both the numerator and denominator by omega n square, and then we have rearranged the terms. The magnitude frequency response is given over here. Magnitude of the numerator divided by magnitude of the denominator. And since in Bode diagrams we sketch the magnitude in dBs, so we shall take the log of this magnitude and will multiply it by 20. So 20 log of this magnitude, that is equal to 20 minus 20 log of this thing. We have taken the inverse of this thing and therefore the negative sign over here. To sketch the asymptotic Bode diagrams, we divide the whole frequency range into low frequencies and high frequencies. So when this frequency omega is much smaller than omega n, so this number omega over omega n, this will be a small number and its square will be further smaller. Likewise, this omega square over omega n square, that will be much smaller. We can ignore this term as well as this term over here, and hence we have minus 20 log of 1, which is equal to 0. So at low frequencies the magnitude response is equal to 0 dBs. At high frequencies, when omega is much higher than omega n, what about this term? This omega square over omega n square, this is very large number compared to 1, so we can just ignore this one. Furthermore, although this is also a large number, but here the power of omega is, what is power of omega? We have omega to the power 4. Omega to the power 4 is a much bigger number than omega square. Here we have omega square and here we have omega power 4. So we can even neglect this term, right? So therefore this expression is equal to minus 20 log of square root of this thing. We have ignored this one because this term is much bigger than this one. Furthermore, we have also ignored this term because this fourth power will be a bigger number, much bigger number than this square term. This square root is cancelled with this square, and then this square over here, that can be taken outside of the log. So we have minus 40 log of omega over omega n, which can be rearranged to write it in this form. So at higher frequencies, the Bode diagram, Bode magnitude plot, that is a straight line. This is equation of a straight line with the slope equal to minus 40, and on the horizontal axis we have logarithmic scale. So that is we have this semi-log graph paper. On this graph paper we have split it into two parts to obtain the magnitude frequency response and for the phase frequency response. First step is to indicate this frequency omega n, which is called corner frequency. Up to this frequency, the magnitude is 0 dBs, and at higher frequencies, there is a straight line with a slope of minus 40 dBs per decade. So to draw a line with minus 40 dBs per decade, we indicate the frequency which is one decade higher than this one, and we shall draw a line with one point over here and the other point over here. So the slope of this line is minus 40 dBs per decade. For the first order transfer functions, we have sketched the asymptotic Bode diagram, and those asymptotic Bode diagrams were fairly accurate. However, for this second order transfer function, the accuracy of this diagram depends upon zeta. So generally we have some peak in the this magnitude plot. So we can even determine the frequency corresponding to this peak, and the amplitude of this peak can be easily determined. So what do you think, how we can determine this peak in this frequency response? How to determine peak? And so you are right. At this frequency, the derivative of this curve is equal to 0. And what is the equation for this curve? What is the equation which describes this curve? The magnitude response is the equation. So with respect to which variable we should differentiate it? With respect to omega. So we should differentiate this frequency response with respect to omega to find the point where slope of the curve is equal to 0. So taking the derivative of this expression with respect to omega is slightly complex. What if we take the derivative of only the denominator polynomial? When this denominator is minimum, at that point this whole thing will be maximum. So instead of taking the derivative of this magnitude, we can take the derivative of the denominator to determine the minimum of that denominator of function. And we can even omit this square root. Why? Because when the term inside the square root is minimum at the same frequency, this term in the denominator, that will be minimum. So at resonant frequency, that particular frequency omega r is called resonant frequency. G of j omega is maximum, and this thing, the thing in the denominator, that is minimum, and also the thing inside this square root, that is also minimum. So we take the derivative of this function with respect to omega, and then determine the frequency, resonant frequency. This expression written in expanded form, square of this plus square of this term minus 2 multiplied by this term, and square of this term is written over here. Now finding the derivative of this function g of omega with respect to omega, that is quite simple. All of you can easily find the derivative. Derivative of this one with respect to omega is equal to 0. Derivative of this term with respect to omega is equal to 4 omega cube divided by omega n square. Omega n is some constant, and then this 2 multiplied by 2 is 4 omega over omega n square, and then 8 zeta square omega n over omega over omega n square. To find the resonant frequency, we substitute this derivative to be equal to 0. That is this thing equal to 0. We have taken omega r over omega n square common from whole of this expression. So we get this thing. So what is the frequency? One solution to this equation is omega r equal to 0. Of course, we are not interested in that particular frequency. And from the term inside these brackets, we have omega r square equal to omega n square 1 minus 2 zeta square. And therefore, resonant frequency, the frequency corresponding to that peak in the frequency response of the system, that is given by this expression. And now how to determine that peak? Substitute this frequency into this expression to get the peak value of the frequency response. So if we substitute this omega equal to omega n multiplied by square root of 1 minus 2 zeta square over here, magnitude of g of j omega comes out to be equal to this thing. You can verify it by simply substituting it over here, which can be further rearranged to write it in this form, and which is finally written over here. So peak value of the frequency response, magnitude frequency response, that is given over here. It depends upon zeta, and for zeta equal to 0, if zeta is equal to 0, how much is this peak value? Infinity. So zeta equal to 0 implies that peak in the frequency response will be infinity, and if zeta is equal to 0.707, then mr will be equal to 1, and if zeta is greater than this value, if zeta is greater than this value, then there will be no resonance, no peak. That is apparent from here. If zeta is greater than 0.707, so the omega r comes out to be some imaginary number, and we cannot have omega r to be some imaginary quantity. Therefore, this is the magnitude frequency response. We can asymptotic plot is simply this straight line and this straight line, and we can improve it by making a peak. We can determine the frequency corresponding to this peak and the magnitude of peak. This can also be determined. For the phase plot, what we see is that if omega is much smaller than omega n, so what will be situation? We can ignore this this term, because omega over omega n will be smaller, its square will be further smaller, so we can simply ignore this term and ignore this term. So 1 over 1 is some positive real number, and the phase angle of the positive real number is equal to 0. So at very low frequencies, phase angle of this complex function, that is equal to 0. At higher frequencies, this thing omega over omega n will be large number, its square will be much larger, so we can just omit this small number. We can even ignore this small number, because this square will be much bigger than this number. So we can ignore this term and ignore this term. And what is square of j? Minus 1. So we have 1 divided by minus 1 multiplied by some real number, positive real number. So overall, what do we get? We get a negative real number, and phase angle of a negative real number is equal to minus 180 degrees. How to draw the asymptotic phase frequency response? At very low frequencies, the phase angle is 0. At very high frequencies, phase angle is minus 180 degrees. So what we do is that we indicate the corner frequency. We also indicate one decade below the corner frequency and one decade after the corner frequency. for the phase plot. So up to this frequency, the phase angle is 0, and for frequencies higher than this frequency, phase angle is minus 180 degrees, and in between these two frequencies we join these two lines by a straight line. So this is the asymptotic phase plot for this second order factor. This peak in the magnitude response, that depends upon zeta. Smaller is the zeta, higher will be the peak. For example, for a zeta corresponding to 0.5, this is the graph. For zeta equal to 0.3, this is the graph, and for zeta equal to 0.1, we have higher peak in the frequency response of the system. So let's take a simple transfer function with some numerical values and obtain its asymptotic Bode diagram. First, it would be convenient to write it into the form which was written in the previous slide. That is, we divide both the numerator and denominator by this 25. This is the frequency response, which is obtained by simply replacing s with j omega, and then divide both the numerator and denominator with 25 to get this expression. And from here we can easily sketch the asymptotic Bode diagram. The corner frequency is 5 if we compare it with the expression written on the previous slide. So if we write the scale over here, it cannot start from 0, you already know it. If this frequency is 0.01, this frequency will be 0.1, this will be 1. Next, this frequency is 2, 3, 4, and 5. This frequency is 5. So we indicate this frequency. Up to this frequency, we have a straight line with 0 dB, and after this frequency, we have another straight line with a slope of minus 40 dBs per decade. So you already know how to draw a line with minus 40 dBs per decade. Simply indicate the frequency which is a decade after this frequency, which is 50, and at 50 this will reach minus 40 dBs per decade. This is frequency equal to 50. So here the graph will drop from 0 dBs to minus 40 dBs. So again, this graph is not very accurate. To improve the accuracy, we can draw a peak over here, and the frequency corresponding to that peak can be easily determined. Also, the amplitude corresponding to that peak can be determined. For the phase plot, we indicate the frequency 1 decade below the corner frequency. So corner frequency is 5, and here is 0.5. Up to this frequency, phase angle is 0, and then you indicate the frequency 1 decade after the corner frequency, and from this frequency onward, phase angle is minus 180 degrees, and then you join it by a straight line. We can also determine the frequency corresponding to this resonant frequency, and resonant peak can also be determined. Zeta is equal to 0.2. Here omega n is 5. So 2 divided by 5, that is, if we compare it with that standard expression, that is 2 zeta into 2 zeta. So which is zeta comes out to be equal to 0.2, and the resonant frequency, we substitute zeta equal to 0.2, omega n is 5, so resonant frequency is 4.79, and resonant peak is given by this relation which we have just derived. We again substitute zeta equal to 0.2 over here, and we get 2.6, and 2.6 will be first converted into dBs. To convert it into dBs, we take its log, and then multiply it by 20. So this thing converted into dBs is 8.3. So we have computed the resonant frequency and also the resonant peak, and therefore this graph can be simply improved by a freehand sketch, and this is the Bode diagram of a quadratic vector. So any question up to this point? So the question is, what will be the use of these Bode diagrams? So up to this point we have not discussed what will be the use of these diagrams. We are only learning how to sketch these Bode diagrams. We shall also learn sketching of polar plots and Nyquist plots, and after that we shall learn how these diagrams can be utilized for analysis and design of control systems. Up to this point we are just learning how to sketch these plots.